As you have already seen, the operational amplifier may also be used as a comparator. The comparator circuit will compare an input signal voltage on one input with a fixed reference voltage on the other input. The voltage of the comparator circuit will be a negative or positive saturation voltage, depending on which input is greater. Op-amps as comparators are also used in Schmitt trigger circuits to clean up square wave pulses. They are also used as zero crossing detector circuits. This circuit will indicate in which direction the input signal crosses the 0-volt reference line. The op-amp as a comparator can also be used as a voltage level detector to indicate when the input voltage reaches a given reference voltage. And a comparator can also be used to generate triangular or square wave pulses. Even though the general purpose op-amp can be used as a comparator, there are circuits designed specifically for this purpose. The LM119 is such a device. Here we see a simple zero crossing detector using the 301 operational amplifier as a comparator. The input signal is a triangular voltage which is being applied across the inverting input. The non-inverting input is connected to ground. The output of this circuit is a square wave pulse that operates between the positive voltage saturation and the negative voltage saturation points. As the triangular input signal crosses the 0-volt reference line and goes positive, it causes the output to saturate at the negative saturation point. When the triangular input signal decreases back to the 0 reference line again and goes negative, it causes the output to saturate at the positive saturation point. In a practical comparator circuit, as the input signal approaches the 0 reference line, the internal noise in the op-amp will cause the circuit to false trigger. This can be eliminated by the use of positive feedback. Positive feedback can be achieved by taking part of the output voltage and feeding it back to the non-inverting input of the device. This will create a variable reference voltage at the non-inverting input because the feedback voltage will depend on the voltage at the output. Resistors R1 and R2 form a voltage divider network at the output of the device. The feedback voltage is taken from the junction of these two resistors. When the output voltage is at the positive saturation point, the feedback signal is referred to as the upper threshold voltage. This occurs when the voltage at the non-inverting input is greater than the voltage at the inverting input. When the voltage at the inverting input becomes slightly more positive than the feedback voltage, then the output voltage will begin to decrease in amplitude. By using positive feedback, the output voltage will drop even faster and it will quickly drive the output into the negative saturation region. This results in a more stable switching action when the output switches polarity. When the output is at its negative saturation point, the feedback signal is called the lower threshold voltage. The device will stay in the negative saturation region as long as the inverting signal is more positive than the feedback signal. When the inverting signal becomes less positive than the feedback signal, then the output voltage will begin to swing in the positive direction. As the output voltage begins to increase in the positive direction, the positive feedback being fed into the non-inverting input will cause the device to snap into the positive saturation point. As you can see, the positive feedback causes the output voltage to snap from one saturation point to the other at a faster rate. This is due to the regenerative action of the positive feedback signal. Thus, the positive feedback eliminates false output transitions. The performance of a comparator circuit can be judged by the amount of time it takes for the device to switch from one saturation point to the other. This time is referred to as the hysteresis of the circuit, and the voltage between these two switching points is called the hysteresis voltage. Even though the positive feedback made the operational amplifier's output switch at a faster rate from one saturation point to the other, the transition time is much too slow for many applications. It can typically be several microseconds. For faster switching times, special op-amps are designed specifically for fast comparator applications. The LM710 and the LM311 are two such op-amps. The LM710 has a switching time of only 40 nanoseconds, and the LM311 has a switching time of approximately 200 nanoseconds. Here we see two precision operational amplifiers. They are the LT1013 and the LT1014. The characteristics of the LT1013 and the LT1014 make them especially useful in such applications as instrumentation amplifiers or any other situation where the op-amp must closely adhere to critical performance standards. These op-amps can be operated from a single 5-volt DC power supply or from a dual polarity power supply with voltages up to plus and minus 22 volts. Their drift voltage is less than 2 microvolts per degree centigrade with an offset voltage of less than 150 microvolts. The open loop gain of the LT1013 and LT1014 are in excess of 8 million with a slew rate of 0.4 microseconds. Each amplifier section will only use 350 microamps of current and can source or sink up to 20 milliamps of load current. The relatively high current consumed by the bipolar integrated circuit amplifier has long been a drawback to their use in battery-powered circuits. Thanks to CMOS technology, a new generation of micro-power linear ICs have overcome this problem. Most CMOS linear ICs can be powered by a single polarity power supply with voltages ranging from 2 to 3 volts. Some devices can be powered by a 1-volt power source. The CMOS operational amplifier has an extremely high input impedance. It also has a unity gain bandwidth that exceeds 1 megahertz, as well as a very high gain factor. As you can see, the CMOS op-amp has a lot of potential. Even though the CMOS operational amplifier consumes very little power, it is important that you realize that some circuits which are designed with the CMOS device can consume nearly as much power as those designed with their bipolar counterparts. This situation occurs when the device is required to drive light-emitting diodes, loudspeakers, relays, or any other device which consumes large amounts of power. When using a CMOS device to drive an LED, it is recommended that you use a high-brightness LED because they will emit a visible red light when the forward current is only 1 milliamp or less. Linear CMOS integrated circuits have the same vulnerabilities as other CMOS devices. The most common problem is electrostatic discharge. Even though many CMOS ICs contain protection circuits that reduce the possibility of electrostatic discharge, these devices should be handled in accordance with standard CMOS handling procedures. Also, unused input pins must be terminated at ground or one of the supply voltages. Unused pins that are left floating may pick up stray signals which cause unwanted oscillations that will greatly increase the chip's power consumption. As we have seen, the operational amplifier is a linear device, and the output of the op-amp is directly proportional to its input. The op-amp has two inputs. One is the inverting input, which is designated with the minus sign, and the other is the non-inverting input, which is designated with the plus sign. The polarity of the signal being applied at the inverting input is reversed at the output of the device. In the same respect, the polarity of the signal being applied at the non-inverting input will remain unchanged at the op-amp's output. The amplification factor, or gain, of the operational amplifier is controlled by the feedback resistor connected between the amplifier's output and the inverting input. We have also seen that the comparator is a linear circuit which has a digital output. Even though the comparator closely resembles the operational amplifier, it is designed to give an output that is either high or low, but never linear with respect to the input. Oftentimes, an operational amplifier with no feedback resistor will function as an acceptable comparator circuit. This part of the video will deal with troubleshooting the operational amplifier, since most modern equipment will contain various types of operational amplifier ICs. A total failure of a well-designed op-amp is rare because input overloads never saturate the circuit. The most common problems associated with the op-amp are hum, drift, and noise. The most common cause of hum is the DC power supply which provides the power to the op-amp. Another common cause is current leakage from other components on the circuit board. If hum or ripple is found at the operational amplifier output, Short the input terminals and check for power supply ripple. Drift and noise are the most common sources of trouble. Even though there are several causes for this type of trouble, the power supply is still the most likely cause. This is due to the fact that operational amplifiers are extremely sensitive to an unstable power supply. When working with op-amp circuits, the power supply should not drift more than plus or minus 1 millivolt on a typical power supply voltage of 15 volts. Another source of noise in the op-amp is the null circuit. The null circuit is also called the zero correction circuit. This circuit takes voltage from both the positive and negative power supplies and inputs a small DC current to compensate for the internally generated offset. Because of the operational amplifier's extremely high open-loop gain, they can be difficult to troubleshoot. If the op-amp circuit uses a feedback capacitor, you can track down hum, drift, and noise by replacing the feedback capacitor with a resistor which has a value of at least 10 times greater than the input resistor. The op-amp's output can be checked with a high-gain scope to monitor the waveform. Another test that can be performed while the feedback resistor is in place is to check the null offset circuit in the IC. Short the amplifier's input terminals and vary the null adjustment while monitoring the op-amp's output with the oscilloscope. As you change the offset adjustment, there should be a corresponding change in the output voltage. If the amplifier does not change the same in both the positive and negative direction, then saturation is taking place in the IC and the op-amp should be replaced.